we're going to move on to quadratic sequences. Now, I'm going to show you how these work. These look deceptively simple, but to find an nth term for them is actually pretty difficult. But I'll teach you, or I'll show you the method that you're usually taught in school, and then I'll show you my kind of different method for this, and with all the reasoning behind how it works. So quadratic sequences are as such. So for example, an example of a quadratic sequence is 0, 2, 6, and then 12, and then 20, and 30, and 42, ... And again, the funky thing with quadratic sequences is you actually only need 3 terms, sorry, to be able to tell you the rest of the sequence. Remember, with arithmetic sequences, I said you just need 2 terms in the sequence to know which arithmetic sequence it is. With quadratic sequences, there's an added layer of difficulty. So you need to know the first 3 terms, or any 3 terms in the quadratic sequence, and you can work backwards to find out what that quadratic sequence is. But of course, with the added complexity, we need to know more terms. So how does it work, you may ask? Well, this is how it works. So we think, what do we do? What do we add from 0 to 2? Well, we add 2. What about 2 to 6? Well, we add 4. What about 6 to 12? We'll add 6, and so on. And what we notice is there's some sort of a weird pattern, right? So we call this the first difference. So we're going to label this the first difference, like that. Okay, so why have I labeled that the first difference? Well, because there's a second difference. Right? We're going to have another line of differences. Right, how is this going to work then? Well, we have this plus 2 and this plus 4. What's the difference? Well, plus 2. Plus 4 and plus 6, what's the difference? Well, it's plus 2. And then plus 2 again, and then plus 2 again, and then plus 2 again. Okay, well, we start to see that this second difference is all the same. Now, let's compare this to an arithmetic sequence. So if we had an arithmetic sequence here, 1, 3, 5, 7, notice if we do the first differences here, straight away, we have a common first difference. So clearly, something's a little bit different here. Something's a little bit more complicated. We're having to go one step deeper into the sequence to find the common difference. It's almost like if you're trying to find the pattern in the sequence, but you're having to dig one step further, one difference deeper down to figure out where it is that you can find the pattern within the sequence. Right. So let's have a think about what's going on here. Well, the first way in which you're taught how to do this is you take this second difference and you divide it by 2. Right, so you divide it by 2. And the number you're going to get here, well, the second difference is 2. The common difference is 2. So you get 2 over 2, and that's 1. Well, what do you do with the number 1? What's the use of number 1? Well, the use of the number 1 is this goes in front of 1n squared. Right, so it goes in front of this n squared here. So you have 1n squared. Okay, so then you say, well, how is this useful? Well, this is how it's useful. So we take our original sequence, 0, 2, 6, 12, 20, ... We compare it to the sequence n squared. Right, let's compare it to the sequence n squared. Now, let's think, what is a sequence n squared? Right, we're going to do this on the next page. Right, what is a sequence n squared? Well, let's say the nth term is n squared. That's what we're saying. So what does this mean? What it means, if we're doing n equals 1 to figure out the first term, then the first term is 1 squared. But notice if we do the second term, it's going to be n equals 2. So the second term is 2 squared. Okay, so what is the sequence? Well, the sequence is going to be 1 squared, 2 squared, 3 squared, etc. Or in other words, 1, 4, 9, 16, 25, etc. Right, and then if we try and write that out here, 1, 4, 9, 16, and 25, and then we try to look at what the difference is between these two sequences. Okay, well, why don't we just take one away from the other? Why don't we just take one away from the other? Right, so let's say our nth term is 0, 2, 6, 12, and 20. The n squared sequence is 1, 4, 9, 16, and 25. So if we do a simple addition, a simple subtraction, right, we can subtract on the left side of this equal sign, and so the nth term, which is what we're looking for, minus n squared, because we're doing it like some column subtraction as if it was with numbers. I know it's strange, but follow me here. And we're going to see what happens. So you have minus 1, minus 2, minus 3, minus 4, minus 5. Okay, so what have I been able to figure out here? Well, I've been able to figure out some new sequence. And this new sequence, minus 1, minus 2, minus 3, minus 4, minus 5. Well, let's think what is this sequence? Minus 1, minus 2, minus 3, minus 4, minus 5. Well, this is a sequence minus n. Right, why is it that? Let's find out. So the nth term is minus n, right? So if n equals 1, the first term is minus 1. That checks out, okay. N equals 2, so the second term is minus 2. Yep, it is. Perfect. So the nth term is minus n. So then we can say the nth term minus n squared equals minus n, because that's minus n on the right hand side. So then if we try to rearrange to get the nth term, well, the nth term is, and we add n squared to both sides, n squared minus n. Okay, so that's a little bit more complicated. Why is it a bit more complicated? We've got this squared term, and that's what makes it a quadratic sequence, right? That's what makes it a quadratic sequence.